Imagine you have a website that stores millions of images. Since there are so many images, it isn't possible to browse through them all. One idea you have is where someone will upload an image and you return some similar images. How would you do this? At first it seems like a very hard problem. After all, similar images could have different poses, lightings, and sizes, and trying to catch every combination would be next to impossible. What if we could turn this into a math problem? One way to achieve this is through nearest neighbor search. First, all the images will be converted into a high-dimensional array, where the dimension is fixed for all images. Now, every image can be thought of as a point in a grid. In 2 dimensions, we are already familiar with this concept, as it is just points to a coordinate grid. Now, points that are closer together to each other can be thought of as similar, and it's just a matter of finding the closest points in a grid. The definition of close is the same as in 2 dimensions. Simply take the squared differences between each dimension and a point, and then take the square root. So to find similar images, simply get several dozen nearest points, also referred to as nearest neighbors. Now, you may think that the problem is solved here, but it isn't. There are a mind-boggling number of images on the internet, and searching through all of them would be nearly impossible. To do this efficiently, we need a strategy, and that's where our work begins. HNSW is an algorithm that is designed to make the nearest neighbor search fast. It is a graph-based algorithm, as it relies on connections between points and navigate between them. The figure here shows how this would work in 2 dimensional space. There are multiple levels of points. Higher levels contain less points, and a point found in a higher level always appears in lower levels. The graph is constructed by adding one point at a time. For each point, the algorithm attempts to connect the added point to its closest neighbors. To get that, a search is performed using a graph. Now, how does the search work? First, we need a point to start the search on. To do this, we take advantage of the higher levels to move to the closest point as quickly as possible. Think about how travel works. You would first take a plane to get close to your destination quickly, which is exactly what the higher levels are used for. Now, once we have a point, we can look at the connections at that point, and if needed, look at their connections as well. We keep track of the closest points, and once we find enough points, we can stop. See here how we only need to explore a fraction of all the points in the graph.
Vimana is another graph-based algorithm for the nearest neighbor search problem, which starts off with a different approach. Vimana starts with building a completely random graph, and then we try to find the global centroid, which is shown as the yellow dot on this graph, and then we locate the actual node that is closest to the global centroid to be our starting node. The main idea is that we start to looking for the best points iteratively from the entry point, which is shown as the node in the red circle. So in each iteration of greedy search, for all the unvisited nodes in the list, only the neighbors of the closest node will be added to the list. So in this case, we assume that the query is part of our graph, which is the yellow dot Q, and then it's also the closest node, starting from the starting point S. So the only neighbor of Q will be added to our list. And here we assume that K, which is the upper bound of the size of the list, is equal to 2, so we have exceeded the amount of nodes that can be contained in the list, so we have to remove the furthest one to maintain the number to be below and equal to 2. On the other hand, the other main function is called robust pruning method, which optimizes the graph on a particular input point. For that, it checks the list of visited nodes and then select on each iteration the closest node to the input point and adds it to the outneighbors of that point. So in this case, as our starting input point is S on the graph, which is the yellow dot, we have 3 candidates, which are the orange dots, and then we only keep the closest point to our starting point. It also removes other nodes that can be reached from the newly added node with the shorter distance. With this repeated process of greedy search and robust prune, the finalized graph should be able to provide a fast search and high recall. So our future work, since we have successfully implemented the two algorithms in C++ with fast runtime and high recall, the next step would be to find a way to potentially combine the two algorithms with their own advantages. We would also like to figure out the differences between these two algorithms and how the differences may be suited for different datasets.